correct.
Well, no, it sounds like your answer is like 7 signigs. Here we go.
Right.
If you
Right.
and if the digits from
But you get this,
I write
zero.
down every
The
single
next
thing that
digit
goes
goes
with
to zero.
Yeah.
So I believe
So it doesn't actually.
that I caught up with all homework solutions to things that did not come out of the book. If there's something that you know that I missed, just let me know, and maybe I'll have time to see it. I think I sent out a couple of homeworks yesterday. I think that takes care of all the homeworks that didn't come out of the book. Over the next couple of classes, we're going to finish up conditional probabilities. So I want to talk about conditional probability density functions, and then we're going to turn our sights towards what can we say about random variables, functions of random variables in this multivariate situation, right, where we have this new random variable which ends up being the sum of two old random variables. That'll probably be Monday's lecture anyway. And then we're going to apply that to a lot of different types of functions. So let me grab some notes here to make sure I know where I'm going. First, I guess we'll make sure, I just want to remind you that with our joint probability mass function, something like that. When I start with the joint probability mass function, then from that I could get a conditional probability mass function, something like the probability of y given x, which notationally we wrote as y given x in this way, instead of just a straight function notation. If nothing else, just to reinforce sort of the relationship between y and x. And it meant the probability of, well, y equals y given x equal to x. And I want to write all this down just because I'm not going to completely justify the continuous case, but just to see that everything is completely analogous. So it is the probability of y equals y and x is equal to x divided by the probability x is equal to x. Right, chapter 1, that's how we can, that's the definition of conditional probability, which now this would be the joint probability mass function with x and y plugged back into it. Right, that's the probability y equals y and x equals x. And then the denominator would be what we would call the marginal probability mass function the marginal probability mass function of y. Let's try that one last time. I had it right the first time. The marginal probability mass function of x, right? The probability x is equal to x. Okay. And then one last step, right, is if I wanted to rewrite this whole thing strictly in terms of the joint probability mass function, how do I write that in terms of the joint probability mass function? How do I get the marginal probability mass function with respect to x from the joint probability mass function? I just sum the probability mass function, the joint probability mass function, I just sum out over all the y's, right? I sum over all the y values. I mean, that's just equivalent to, let's see, with the y's, if I sum over all the y's, that's like summing over all the column entry, or the row entries to get that last one out of there. Okay? So we can actually see how all of this is related back to the joint probability mass function. It's just the values coming out of the joint probability mass function divided by what I get if I sum over the row that I'm interested in this case, with respect to y. Okay. So sometimes we'll like to think about it like this, and sometimes we'll like to think about it as that. In the continuous, right? So in the continuous case, when I'm dealing with, x and y, two random variables that are continuous, then I end up with a joint probability density function. Looks like that f of x and y. And then if I want to deal with the conditional probability density function, I keep it in the same order, y with respect to x, it's going to mean the analogous thing, right? Up here, this is the probability of y given x. And I'm gonna mention this several times today, and it'll stick hopefully one of these times. When I think about something like this, what's the probability of y given x? I think about x as being fixed. I mean, it's not fixed in the sense that it could never change, but I'm asking the question, okay, what's happening with y for a given x value, for a fixed x value? And then later on, I could say, well, now what's happening with y for a different x value? Okay, now what's happening with y for a different x value, right? But I do think about x as being fixed in that, which is maybe another reason why I wouldn't use the standard function notation, because given this, fixing this, I'm asking a question that is basically a probability mass function with respect to y. Okay. So I'm gonna repeat that over and over again because it's gonna help us hopefully understand all of this. So again, it's really this question of this joint probability density function is the likelihood of different x's and y values appearing from whatever experiment, whatever random variables generate this situation that give me this particular joint probability mass function. But when I talk about conditional probability, I'm really thinking for a given, for the moment I'm going to think about x as being fixed. Now I want to understand what's the density, the probability, the conditional density of y given that particular x value. Okay. And I'll just give you the punchline, right? Is it's going to look exactly like the equivalence over here. That is, it'll be the joint probability density function of x and y divided by the marginal probability density function of x. And of course, how do I compute the marginal probability density function of x given the joint probability density function? How do I go from this to that?
Maybe the integral over the y values?
Yeah, integral over the y values. So we're going to start with an example from scratch and go through it. Yeah, this would just be the integral over all possible, negative infinity to it, over all possible y values f of x, y. I'll integrate over the y's, right? And that would give me the marginal probability density function of x. Right? Again, the difference being this, or this, right? These are telling me probabilities, and then these are telling me likelihoods. Likelihoods of being in certain regions, not explicit. Right? If I integrate over y values, then it would be telling me probabilities. All right, so let's give ourselves an example, and so we'll have one main running example through all of this, and it actually comes from. It was in section, I want to leave a little space. In section 3.3, it was example D. I'm pretty sure we did not talk about this particular one in class, so we'll just start with it from the beginning and just go through the whole thing. But in this one, I'm given a joint probability density function as lambda squared e to the negative lambda y. 0 less than or equal to x less than or equal to y. So that's my joint probability density function for this. I have these two random variables, x and y, and however else they work, right? They're two continuous random variables. Somehow when I start, sampling from these two random variables, and then I start plotting the points, it should start giving me something that looks like this function right here. And it's important to note that even though I can break the x's and the y's up as the function, as the product of two functions. This is not going to be come from an x and a y value that are independent of each other. Okay. Right? There's certainly a dependence, and it's not from the function part of things. We had talked about this before. It's from the region part of things. Whenever you're dealing with a joint probability density function, you should think about not just what the function is, but where it's defined. And so here it's telling us that this would be telling me what? That my x and my y values are both going to be positive, which means I'm over here in the first quadrant. And then additionally, that y is greater than or equal to x, so I must be interested in this line y is equal to x. So I'm in the first quadrant, this line y equal to x is a dividing line, and I want y is greater than or equal to x, which means I'm up here in this region right there. So again, with all of these things, it's not just the functions that we're dealing with, it's the regions on which they're defined. I'd say this is half the battle, right? Figuring out what region we are in and sort of how am I going to work with that for a lot of these computations. So, let's see. So that's my function. And okay, so how do I know, for instance, that this function doesn't come from independent random variables, right? Because the boundaries depend on each other, right? The boundary, this boundary here, which is the boundary of my region, has a dependence between my x and my y values. Okay? If I'm in any situation in which I have independence, my function should be the product of the two marginal density functions, and it should be defined over some sort of a rectangular region. And of course, rectangular region could mean infinitely long rectangle, right? I mean, the first quadrant would be a rectangular region, or we saw an example where we dealt with something like this, which was in a rectangle that went off to infinity, things like that, maybe between 0 and 1. But what I really don't want to have, I don't want the boundaries to be dependent on both x and y at the same time, certainly like they are here. So not independent. We'll be able to see that in a moment because we'll calculate those marginal probability density functions. But let's go ahead and do that. So let's compute the marginal probability density function with respect to x. And so we said we could do that by integrating our joint probability density function over all the y values. So again, right, think about it in this way, that think about x as being fixed. And of course I can change it after I'm done, and I could just say, okay, well, it's this for this x value, and it's this other thing for this other x value, and it's this third thing for this third x value. But I just for the moment want to think about it as fixed, because I want to think about this thing as being fixed, and I'm integrating over a particular y value, or over all of the y values. Right? So I have this x value here that I'm going to think of as fixed, because it's going to help me figure out my boundaries. So if x is fixed and I want to sum over all the y values, then it's saying I'm really just interested in this vertical line. And if I'm going to be interested in integrating over that vertical line, I'm probably just interested in where that vertical line takes non-zero values, which since it's taking 0 values down here, it really means I'm interested in that vertical line up there. So when I go ahead and actually set up this integral, what I'm actually interested in is my function, lambda squared, e to the negative lambda y dy. And I'm integrating in this y direction, in this vertical direction, and at the bottom of this is y equal to x, and at the top it's y equal to infinity, right? Or y equal to b as b goes off to infinity, but we'll just write y equal. So it's going to go from y equal to x, right, because I'm integrating with respect to y, to infinity. I oftentimes will write, the variable, at least on the bottom one, just to remind ourselves that I potentially have I have multiple variables running around, but I want my y value, I'm integrating with respect to y. Y is going to range from y equal to 1 at the bottom, y equal to x, to y equal to 1 at the top, y going up to infinity. Right. And again, if I think about x being fixed and I just draw one in there, and then I can draw my vertical line, that would be, I'd be summing the y values over, Riemann summing the y values over, then it hopefully helps me figure out what those limits of integration are. And then the rest of it is just a pretty straightforward Calc 1 or Calc 2 question, actually Calc 1 in this case, because I would get this lambda squared e to the negative lambda y, antiderivative with respect to y, antiderivative of e to the negative lambda y is e to the negative lambda y over negative lambda. I just did that in my 112 class this morning, but not with lambdas, with k's. And again, y equals x, y equal to infinity. Okay. And then I could go through and I could plug in my y values. And if I plug infinity in for y here, what's e to the negative infinity? 0, right? E to the negative infinity is 0. I'm just going to take that, and then minus, and then if I plug x in for y, I'll get a negative, let's see, lambda here and lambda squared will cancel with one of them. That negative I'll just bring out in front there. So that becomes a negative lambda e to the negative lambda y. Now I'm going to plug in y equal to x, and I'll get a negative lambda e to the negative lambda x, okay, which will give me, I guess, lambda e to the negative lambda x. So that would be my marginal probability density function. Well, almost. I should figure out which values what value x is can I fixed x, right? And so that's what I would get given a fixed x. Now that x could be different values. What values can I use for x in this case? Yeah. This is telling me x has to be greater or equal to 0. So that's what our marginal probability density function with respect to x would be. And by the way, then what does that tell me about the type of random variable x is? I mean, that's one of our named random variables, and since we only have about 4 of them in the continuous case, which random variable gives me lambda e to the negative lambda x as its probability density function?
Exponential?
Exponential with, I need to say the parameter with, what's the parameter for that? Lambda, right? Exponential parameter lambda will give me this. So I can understand how the x values for this joint distribution are spread out. They are spread out like they're sampled like an exponential distribution with parameter lambda. Okay, good thing to know. And so we could do the same thing for y. And then we're gonna calculate some conditional probabilities after that. But let's just do the same thing for y. We're gonna calculate the conditional probabilities of y with respect to x, which we have all the information now to do that. But we'll also do x with respect, or x given y. So y given x and x given y. Let's figure out this other marginal. Also help us figure out, okay, how does this work? So now I'm going to integrate from x ranging from negative infinity to infinity, my joint probability density function of x and y. And I'm going to integrate over all my x values. So again, now instead of fixing an x value, now I'm going to have a y value, right? Now I'm going to think about, okay, given a y value, I want to sum up over all of the x values, which means I have this horizontal line. And of course, I'm only interested where that horizontal, right? Summing over that horizontal line where I get non-zero values, right, which would be in that region. So I'm going to think about now my y being fixed, or at least, I have this y value, and now I want to sum over, Riemann sum, integrate over all of the x values. So here I would be integrating from x equal to what at the bottom to x equal to what at the top? Y. But draw a picture, right? Just think of, but I'm going to keep reinforcing that fixed, right? Fixed, that I do this calculation for an x, but of course I've done this, the first time I did it in such a way that when I'm done with it, now I can just, you just give me the x and I can immediately tell you what the answer is, right? That's the whole point of this. But I just want to emphasize, we're not thinking about x and y as both changing at the same time, right? X is what it is, and now we're summing over the y values. Because again, once we figure out these limits of integration, of course we could work with uglier functions if we wanted to, but given the functions that were usually exponentials and constants and some polynomials and stuff, they'll get worse, right? We'll get back to normal distributions in the not too terribly distant future. Probably next Wednesday we'll be back with normal distributions, and that's an e to the negative x squared. That's a messy one, right? But for the most part, these types of questions, as soon as I figure out the limits of integration, that's over half the battle at the very least. And so I would have my function, which is lambda squared e to the negative lambda y, and now I'm integrating over all the x values. And now what is the antiderivative of that with respect to x?
That times x.
Yes, that times x, because this is not dependent at all. This is like a constant with respect to x. So it's the antiderivative of a constant, which is the constant times x. Right? Unlike here, where I had to take the antiderivative with respect to y, and of course this is a function with respect to y, and it has an antiderivative function. But now with respect to x, this whole thing's behaving like a constant, and then the antiderivative would be x times that. And then I'll plug in my x equal to 0 and x equal to y. Okay. And then I see something like, when I plug in my y, lambda squared e to the negative lambda y times y, I'll write it as lambda squared y e to the negative lambda y. And when I plug in 0, it's just going to be 0, so it's going to be lambda squared y e to the negative lambda y. And again, y can, I picked a y value and that's what I get. Now I can pick any other y value. Which y values are valid to pick here? What's that? Yeah. Y greater than or equal to 0, right? Going off to infinity. Okay, I can pick any y value as high as I want. And given each one of those. So again, that's the way I'm going to think about this. And by the way, what does this tell me about my marginal, right? What sort of random variable does y come from? That's one of our named random variables. And it's not uniform. It's not quite exponential, right? Because I have this y here instead of just an e to the negative lambda, and there's a lambda squared. But which one is this? That was one of our gammas. With alpha equal to, remember, gamma distribution with an alpha equal to 2 has 2 parameters and a lambda. And I will point out here that exponential random variables are also gamma distributions, right? Gamma random variables, where I could have called exponential with parameter lambda, I could have called it gamma alpha equal to 1 lambda. Gamma, it's been a while since we talked about it, and we haven't really brought it up much since then, but a gamma distribution was a generalization of an exponential random variable, where if alpha is equal to 1, it's just the exponential, but with alpha equal to 2, right, it's then 3 and 4 and 5. Actually, it's the idea of having repeated gamma distributions. We'll actually see that today with all of that. Okay. So I can calculate both of those the marginal probability density function of x and the marginal probability density function of y. It's just saying if I want to understand how these values are distributed along the y-axis, then I could just draw from a gamma distribution with alpha equal to 2 and lambda being lambda, and that's how I'm going to pick a y value out of this. Okay. Now I don't just get to draw from an alpha from a y, from a gamma, and then from an exponential, and just put them together, because these two things are not independent. If they were independent, then I would just say, okay, let me just find my exponential distribution, right? Sample from this, let me sample from this, and I'll just put them together as a point x, y here. Okay. That's what I could do if they're independent, but they're not. My x values are dependent on my y values are dependent on my x. Okay. I can see that in the regions they're allowing me to take. So, yes?
So if we integrate either of the marginal probability mass functions, can we get the marginal from the distribution functions?
No, so you're saying if we integrate the marginal, so if you integrate this from what to what?
So
From 0 to BA or something like that?
yes.
Or from negative infinity to A, right? Yes. So if you integrate, so this is just like chapter 2, right? If I want the Fy of, I'll just call it B, I will integrate from negative infinity to B this F of Y, B. Yes, that's true. Yes. Yeah. Just like before. It's just, these are probability density functions now in one variable. Essentially by summing over all the x values, we're throwing away the x values. Actually, we're not throwing away the x values. Essentially, we're taking all the possibilities here of how likely things are to occur, which have to do with this height of the function that's sitting over the top of this, and we're projecting it all back to the y-axis. We're just we're throwing away the x value and we're just putting it back on the y-value axis, and then they'll give me a probability density function just strictly in terms of y. Okay. Which is different than what we're going to do over here. So now we'll make our transition over to the, our conditional probability. So is this the one I want to calculate first? That's really narrow. Yeah, that sounds good, okay? Let's see, so let's figure out the conditional probability of y with respect to x for this particular case. Y, I'm sorry, not with respect to, given x, right? Y given x. Y given x. It's the joint probability density function divided by the marginal probability density function with respect to x. There we go, of x. My joint distribution function was lambda squared e to the negative lambda y. My marginal is lambda e to the negative lambda x. The values that I'm interested in, again, think about this as a fixed x, right? Given some value for x, I'm asking the question, you know, what's the probability density function for the y values, right? What does this tell me about that? Given a certain x value, so now I'm back in this situation again, right? Given that this occurred, what is the probability of my y value being here versus my y value being here versus my y value being way, way, way up there, right? Versus my y value being down here. By the way, what's the probability of my y value being down here? None, right? Because it's not part of my region. That would mean I'd have to, given this x value, right? This couldn't possibly occur because it's outside of, at that point, it's outside of the region. Okay? But the height of the function here, and the height of the function here, and the height of the function, right? Those would tell me the likelihood of being maybe in this region versus this region, so on and so forth, which is what this function right here is telling me. So given a particular x value, and I can change that x value later on, what's the likelihood of getting different y values? And I can simplify this. Let's see, I have a lambda and a lambda squared. So that lambda squared one of those lambdas can cancel out with that lambda in the denominator, and I can actually, I can move this up to the numerator, and I could write this as, I guess, lambda e to the negative lambda, and I could write that as a y minus x. And then I could ask the question, okay, well, for what y values is this function defined? Or for what x and y values? And I do know x has to be greater than or equal to 0, but what's true about y?
That's greater than x.
Yeah, y has to be greater than or equal to x, right? So my y has to be greater than or equal to x, and of course they both have to be greater or equal to 0. But again, given a particular x value, fixed or use that word given, right? Given a particular x value, then this function here is telling me the likelihood of ending up with different y values. Oops, that was a lambda, not an x. Okay. And now, if we look at that, what sort of random variable does that look like? Sort of look like. Sort of looks like, kind of looks like an exponential. You know, I'm thinking of my x as fixed, right? So again, it's important to think about this as, you know, given a particular x value. So if I do a change of variables here, if I let t equal to y minus x, right? So this y, you know, I have this y value, and I'm going to subtract x off of it. X is some number, right? I'm going to subtract 10, I'm going to subtract 13, whatever I decided I wanted my x to be. Then I could rewrite this as lambda e to the negative lambda t. And then, let's see, if y has to be greater than or equal to x, means y minus x has to be greater than or equal to 0, which would just tell me that t has to be greater than or equal to 0. Doesn't that look exactly like an exponential random variable? Yeah, I mean it is. It's the probability density function for an exponential random variable. Okay. Let's see. So somehow this is an exponential function for a random variable, but everything's been shifted, right? Instead of, let me make sure here, right? Instead of just taking my exponential random variable, what I'm really interested in is my y. Let me put it back again. And y is equal to, let me bring this over to t plus x. So I can understand what's happening with y, right? I'm going to draw from an exponential random variable, and then I had this fixed number, whatever it was, I'm just going to add it to it. Does that make sense? I mean, that's all that's happening right here, because again, if we don't think about x as being fixed, then it seems like x's and y's are changing at the same time. But once we've started this problem, we really are, given x, given some value for x, what can I say about y's? Well, here's what I can say about y's, right? It looks like I can draw from some exponential random variable with parameter lambda, and then I'll add this number, whatever my given was, to it, and that's going to be my y value. Okay? And that's how I could now generate the y values out of this conditional probability. And of course, if I want to use a different x value, then I could use that different x value. I would generate from an exponential random variable, I'd add that new number to it, and that would be my new y value, right? And so on and so forth. Okay. So notice, right, we have this conditional, the y given x looks like, and it is an exponential random variable, just everything's shifted up by whatever number I pick right here. I'm just going to add a constant number to it. So now let me put it all together. Okay. Because not only, not only can I compute my conditional probabilities in this way, but I could take a formula like this and I could rewrite it. And I could write it as f of xy, right? The joint probability density function with respect to x and y is equal to f of x times f of y given x, y given x. And this is the sort of formula that goes back to chapter 1 again. It's the continuous version of that. Things like, if I want to know the probability of A and B occurring, or A intersect B, right? I could calculate it by the probability of A times the probability of B given A. I lost the name of that when we were talking about this sort of thing on Wednesday, but that was called the multiplication principle, right? If I want to know what's the probability of A given A and B, well, it's just the probability of A times the probability of B given A, right? And the nice thing about something like this is it allows me to compute the probability of these two things together by breaking it up into these two smaller experiments, right? First is, what's the probability of A occurring? And now that we know the probability of A occurring, what's the, given that A occurred, I say it that way, what's the probability of B occurring? So it lets me take this situation and break it up into first this and then that, right? First this occurred, and now given that that occurred, what's the probability of that occurring? And notice that's what we're doing here. If I want to understand this joint probability density function, which involves both x and y occurring, or possibly occurring, right? Likelihood of them happening. This is saying, okay, well, how likely was it that x occurred? And now given that x occurred, how likely is it that y occurred? Right? So it's the equivalent to what we have down there. And notice, it's saying if I really wanted to generate something, an experiment, that would lead to the probability density function that I see right here, which is what I see right here, in all its messiness. It says, okay, first of all, I'm going to pick my x this way. I'm going to draw it from, what's x? I'm going to draw it from an exponential distribution with probability lambda. So if I really want to understand what's going on with the experiment that gives me this joint probability density function, I could, there's a exponential random variable sitting over the top of x. The first thing I could do is I could pick a value for x from that probability density function. And then, okay, so this x will come from an exponential random variable with some lambda. Okay. And then, given that x occurred, right, so now I picked a number over here for x. So now given that x occurs, I'm going to pick a y. How do I pick my y? Well, I'm going to pick a t, call it t, right? I'm going to pick a t that's going to come from an exponential random variable with probability lambda that has nothing to do with the other one, independent at this point, right? Just some exponential random variable, and then I'm going to take that t, my y is going to be that t plus x. Right? Which x? Well, that x that I found already. And that if I want to know how to populate this probability, this joint probability density function, I'm going to pick an x, and then what am I going to do? That's going to give me my x value, and then how do I get my y value, right? I'm going to use that x plus some other exponential random variable that's not related to the first. That's going to come from that, and that's going to give me my, xy value, or I could write it x plus t value. Okay, that would end up going in this probability density function that would occur as likely as I expect it to occur. Which is really telling me what? Is somehow this y, which I've already said is a gamma distribution with alpha equal to 2, and lambda, right, the given lambda value, somehow looks like it's also part of the sum of two exponential distributions, which I knew that was true already. So really, you can think about this, this is exactly where this probability density function could come from. I'm going to generate a value for x that's going to come from an exponential distribution with parameter lambda. I'm going to generate a second value from an exponential random variable with parameter lambda, I'm gonna call it t, and then my y is gonna be that x plus t. And that's how I could end up with this probability density function. All right. So, again, I'm gonna take this big two-dimensional thing, and I'm breaking it up into two simpler experiments. First, I'm gonna figure out what x is, and now given what x is, I'm gonna figure out what y is. Okay? And it's gonna be one way to think about that, that big experiment by breaking it up into these this two-step experiment. Now, let's do it the other way. See, we are done with that part of it. Now let's figure out what the probability of x given y is. And 8 minutes should be plenty of time for that. Okay. Right, because not only can I think about calculating this in this way, but if I wanted to, I could think about the probability of A and B as being the probability of B, and then the probability of A given B, right? So I could take this more complicated experiment that gave me A and B, and I could think about it as, okay, first A occurring, and now given A occurred, what's the probability of B? Or I could think about it, okay, B occurring, turn it into a different two-step process, and now, given that B occurred, what's the probability of A occurring? Right? This is the basis of Bayes' theorem, which says sometimes more or less, sometimes it's easier to calculate one or the other of these, and then we could use that, they're related in this way, and they're both related to this, to figure out a conditional probability that maybe isn't quite so obvious. And so, so what it's saying here is, not only can I compute the joint probability density function in this way, but if I wanted to, I could think about this thing coming from the joint probability density, the marginal probability density function of y, times the conditional, right? The conditional probability density function of x given y, of x given y. So yeah, I can think about it as this exponential distribution and this second exponential distribution that leads to my ordered pair in that way. But somehow there should be another way to think about, well, maybe first I'll pick a value on the y-axis, and then I'll figure out how to use that to pick a value that's going to go in the x direction. So let's just go ahead and do that, because it should be f of xy divided by f of y. And I know this all comes at you at 1,000,000 miles per hour. Go back and rewatch it again. It's like, oh yeah, I understand, right? But I know it comes. I can see some people's eyes. You kind of sometimes look like deer in headlights. Sometimes, but right, it's just this idea that I can think about this experiment occurring in the opposite order. So first time I picked a value here, and now given I picked a value here, how do I decide the y value? This time I'm going to decide on the y value first. And now that I've decided on a y value, how do I pick an x value? That's exactly what we're calculating right now. And the answer is, well, let's see what the answer is. Lambda squared e to the negative lambda y over the marginal probability density function of y, which was down here, is that one right there. Which is lambda squared, that was from our gamma distribution, y e to the negative lambda y. And here y had to be greater or equal to 0. Again, here I'm thinking about y being fixed, at least for the moment, and I'm trying to ask some questions about x. So what's going to have to be true is y has to be some positive number, and then x has to be some number that's between 0 and y. So 0 less than or equal to x less than or equal to y. And I can clean this up. Lambda squareds cancel out. E to the negative lambda y cancels out with e. That's nice, right? I get 1 over y for x between 0 and y. And which of our named random variables is this one? And I have to keep emphasizing, I told you 6 times, right? Here, y is constant. Y is a fixed number, so 1 over y is a constant. So what random variable is this?
Uniform.
It's a uniform. What's the parameters on that uniform random variable? 0 on the bottom and 0 to y. Certainly it's uniform and uniform is dependent on y, but it's a uniform random variable with that value y, right? This is, if I had 0 to b, then it'd be 1 over b, right? Something. So this, again, y is fixed. Given that y is fixed, or that, given I have a y, which means I'm thinking of at y being fixed, this is just a constant. Okay, it's certainly a function of x, but it's a constant function of x, and that's what we call a uniform random variable. Okay, so in this other direction here, here's what we're going to do. So we can get this big experiment that comes from the joint probability density function by now first selecting our y value. And how do we pick our y value over here? It comes from we wrote it down to start with. Y comes from a gamma distribution with alpha equal to 2 and lambda equal to lambda, whatever the lambda is. Okay. So I can first pick my y value here, and it's going to come from this distribution. Okay. And then once I get my y value, let's just say that y value right there, I can now get my x value. How far do I have to go out along this? By using this, which is now pick a uniform distribution. Just pick all the numbers uniformly between 0 and y. Which means what? Just pick, use your little calculator, whatever you have there, pick a random number uniformly distributed between 0 and 1, and then multiply it by whatever your y value was to begin with. Right? And that's how you can get a uniform distribution between 0 and y. And so you could do it that way, right? So you could get something from a gamma distribution, and that will give you your y value with a 2 and a lambda there. And now given a certain y value, you're going to pick your x from a uniform distribution from 0 to y, right? Pick your random number between 0 and y, and then that now will give you your ordered pair x, y. That will be, the various points that you could have in here. So again, I have this big joint probability density function, and the question is, how do I try to understand what's going on with these two random variables and how they're related? And again, we're just using conditional probability. If they were independent, that's great. I just do something and I do something else, and those would be my 2 points. But no, it's more complicated than that because x and y are dependent on each other. So what we've done is we've broken this up into 2 different experiments. We say, well, the first thing we could do is we could find an x value, right? And now that we found an x value, right, given that I find an x value, I can now find a y value. Or, right, we could go the other way around. I could first find a y value, and then given I found a y value, I find an x value. And it's going to help me understand these 2 things. So I can either generate this random variable by doing an exponential distribution, find an x through an exponential distribution, and then finding a y through an exponential distribution and adding that number, right? And that's one way to get that. Or the other way to think about it is just go straight to the gamma distribution. That would be my y value. And then now that I have my value for y out of a gamma distribution, now I'll go ahead and figure out a value for the uniform distribution. By the way, this is not something I would have necessarily, that would be, you just guess. It's like, oh yeah, everything's going to be uniformly distributed there. I wouldn't have necessarily have thought that ahead of time. But I could perform that experiment and I could get values up here in that way, and it turns that the density of the values you get out of those 2 different experiments would be identical, and they would be identically equal to that one right there. So, we're going to stop right there. I'll give you 1 or 2 problems. I know I have 1 problem I definitely want to give you for homework out of this. Probably a second one. Going back over the last couple of homework writing up solutions, I realized I've been giving you guys a lot of problems. So I'll make it a little bit lighter tonight. But this idea of, just think about this conditional probability these probability density functions is, again, taking more complicated things and breaking them up into two-step problems. At least that's what we're doing right now. And so what would you have to do in the first step? What would you have to do in the second step to get this big experiment? And then, yeah, not only could we do it that way, but we could switch the order and then go from there. And that is, again, that switching the order is the basis of what's called Bayesian analysis, where it's sometimes easier to understand things from one direction, but you really want to try to understand them from the other. All right, we'll stop there. And yes, I do realize